Uh, my name is Dragan Djuric, and I'm going to talk about some Clojure and some high-performance computing. So this talk, these slides you can find at my blog, dragan.rocks, and also you can find many articles there about the libraries that I'm going to mention today. So all the articles are self-contained tutorials. You can try them in your Clojure REPL. And libraries are usually open source at uncomplicate.org. So everything that I mentioned you can try at home, and I hope you will. So we all love functional programming. We all love Clojure here. I will just skip this slide. No, not again. Huh. Okay. But I suppose most of you haven't tried much about GPU programming or high-performance computing or low-level programming. So I will spend more time there. So what is number crunching? According to Urban Dictionary, it's only thinking about the money and the fame and attention. Okay, functional programming and number crunching and Clojure, I hope, are sometimes used in financial software, but everything else, not so much. And a number cruncher, also according to Urban Dictionary, it's a computer that can solve many problems at a fast rate, which is a bit, it makes a bit more sense than the previous definition. But how fast is fast? So we all, when we talk about some technologies, sometimes JavaScript is fast, sometimes Java is fast, sometimes C is not fast enough. So how fast is fast? When we talk about speed, usually some things that we use run in milliseconds, which is a blink of an eye. For a human, it's not so much. But then again, in some other application like high-frequency trading, 1 microsecond could be a big deal. And when we are implementing low-level numerical algorithms, then maybe a nanosecond makes a difference on the level of one operation. So it's a bit relative. But in any case, many nanoseconds make a megasecond. So the point is here, I'm not talking so much about big data, although it is related to big data also. But I'm talking more about big computation. So regardless of whether you have lots of data or just a bit of data, I'm talking about cases where you have to do a lots of numerical computations over that data. And it means billions and billions and billions of cycles of floating point operations. So I'm mostly talking about numerical data and numerical algorithms, and that data is usually some floating points arrays. So is Clojure and functional programming good at number crunching? Well, it's not. And is Java good at number crunching? Well, it is not bad, but it also not very good. It's not very good because we don't have access to many hardware-specific optimizations. But on the other hand, some techniques from functional programming and some things that we use every day are very useful when we are writing numerical computing algorithms. On the other hand, some other platforms that are more popular when it comes to number crunching, such as Python, for example, are also on themselves not very good at number crunching. I mean, Python is awful at number crunching, but the point is, it's so awful that people actually implement all the algorithms in C and then just call it from Python. And it's very, very useful, and there are many, many people using it much more than the functional programming community is. But the trick is that if you want to implement something or change something or improve something, you have to work on the lowest level C or C++, and then just call it from Python. So the knowledge of Python is not enough here. And the CPU itself is not that good at number crunching because it has so many features that it has to spend lots of transistors on the features that are not really used in number crunching. And then on the other hand, it has to dedicate less transistors, less hardware to the actual operations for floating point operations. So, graphical processing units help a lot with that. Why? They have many, many really not very featureful cores, but these cores have exactly those features that we need in number crunching. And also they support massive parallelism, which has many relations to functional programming. The point is, and the problem is that the programming tools are really awful and really difficult to work with. Even if you are not a beginner, you don't have to be a beginner to have trouble with these technologies. So I developed some libraries that hopefully help with low-level programming of graphical processing units or accelerators or even CPUs, but gives you a nice high-level tools to work with them. And what is the key point is in this talk that they enable us to program in interactive way. So if most of you, I hope, tried Clojure, and how do we program in Clojure? We open the REPL and just dynamically build our application. There is no phase of writing lots of code and then compiling it and then try whether it works. No, we just start the REPL, we have some tests, we write some more, we write some more code, and our application grows, and we can experiment a lot and learn the API, learn the libraries, learn the tools. So that's the point of these libraries. These are all open source. You can find them at uncomplicated.org. So let's start with some practical things. First things first, how fast is fast? The first question from the start of the talk. I will walk through one of the simplest numerical algorithms, which is dot product. It's a building block of many many numerical computing algorithms. And there are two key techniques from functional programming that build this dot product. These are map and reduce. Actually, we compute dot product of two vectors or arrays by multiplying each pair of elements and then summing all these products. We get one number as a result. And of course, any Clojure or functional programmer will easily write a one-liner, which is map over x's and y's, and then reduce by plus. So it's a simple function, really elegant solution. It computes a correct answer. It's easy to use. And on two Clojure vectors of 100,000 elements each, it takes 14 milliseconds to compute on my desktop. So it's quite fast. But remember that these function is just a building blocks of larger algorithms. We never need to compute dot product on itself. So let's try to speed it up. If we use Neanderthal, there is a dot function. So we just call this function over to primitive vectors of the same size. And on my CPU, which is, I think, 4 years old or 5 years old, it's 6 microseconds for 100,000 elements. So it's 3 orders of magnitude faster than the Clojure version. And what about GPU? How fast is it? Also in my desktop, I have NVIDIA 1080 Ti, which is a rather recent card, maybe 2 years old. The same API, so Neanderthal supports GPU transparently. You can use the same code to run the dot product on the GPU. The answer is the same, and the time is 26 microseconds, which is slower than the CPU. So what's the issue here? We accepted something even faster. Well, let's try a different experiment. Another basic linear algebra function is matrix multiplication. We have 2 matrices. We get the third matrix as a product of these 2. Each element of the third resulting matrix is actually a dot product of the corresponding column of the first matrix and the row of the second, or the other way around. It doesn't matter here. The point is, if I take 2 matrices of 1,000 elements by 100,000 elements and multiply them, I will get the result of 1,000 times 1,000 matrix, which is a 1 million element matrix. To compute this multiplication, I need to do 1 million dot products of 100,000 elements. So it's quite a lot of computations. So on my GPU, it takes 23 milliseconds, which is 23 nanoseconds per one huge dot product of 100,000 elements, which is, if we compare this speed with the starting Clojure speed, it's 600,000 times faster. Of course, it's a bit of comparing apples to oranges, but still, it gives us the reference of the speed that we got, and the way that we manage this is we actually fused a lot of operations into one. So whoever implemented these operations could use a lot of optimizations, so it's actually 1,000 times faster than the solo dot product. Okay, I'm not running out of time, which is good. So, this is one case. We are using a nice library with high-level API to call some high-performing functions that someone already wrote. But in real life, there is always a part of our software that no one have written before. So we have to write it. And we have some special needs, special features that we want. So instead of writing in C++, in thousands or tens of thousands of lines of C++, the idea of these libraries is that we can write most of those in Clojure interactively and combine it with the functions that we already have. So I will show you a quick walkthrough, and this presentation is generated from the live REPL code, so from org mode. So it's not copy-pasted, it's actually, if you type these things in your REPL, you will get the same results. So let's try it with CUDA. Of course, you have to have the hardware. First things first, we initialize the environment. It's something that CUDA requires, and we get the result. Okay, it's initialized. It has been initialized well. So I will call another function to see how many of devices I have in my desktop. In case of my desktop, it's 2. Another simple thing that I can do just to explore the API is to take a handle of the first device and put it in some Clojure var. I will get it in my REPL. It's ready for future use. Now, I would like to see what are the capabilities of my graphic card in this computer. I get a nice map of all the info. Of course, I didn't show everything because it couldn't fit on the screen. But the important thing is that my GPU has 28 physical cores. Each core can run 1024 parallel threads. It has 11 gigabytes of RAM and supports compute capability 6, which is basically something like a CUDA language version. Now, it is not enough to do this, to write the program. Another thing, the starting point of our program is the context. In context, we actually set up the hardware that we have in our computer. So this device that I instantiated, now I use context to say how I will use this device. I can just create a default context by calling a context function. And I can also get the info of this context. And default context may be important. The important thing is that API version is 3.2, so it supports some older CUDA version code. Of course, I can change it. And another important thing is, no, all of these are not so important for us now. I can also check whether the current context that CUDA maintains is actually the one that I got. It says yes. And now to the real deal. So, in our functional programs, it's easy to look at the program as data and the functions that work on the data. And it's similar to with CUDA way of programming, but instead of hash maps and vectors and whatever data structures that our language supports, in CUDA usually, and OpenCL and another GPU programming techniques, we usually use and work on row arrays, either byte arrays or floating point arrays, but row arrays. And all functions usually work destructively. That's the main difference with functional programming. Another important thing, GPU has its own memory. So I have to work with main memory and the memory of the GPU to somehow synchronize the data. I create an array on the GPU. I create an array in my Java virtual machine. Let's check. Okay, in Java, it's array of consecutive numbers. Now I have to transfer the data ClojureCUDA handles this automatically. Just give it two arrays, it will find a way how to transfer them optimally. Now, I cannot access specific elements on the GPU directly, at least not efficiently. So I have to transfer data back to see whether it's correct. Okay, it is. Now, the real deal is, this is the only thing that you have to write in C. And it's a subset of C, so no complicated C++ tool chains or anything else. The kernel is actually the part that is running on the GPU. Everything else is running on the CPU in Clojure. So a small percentage of code would be a code like this. This is the kernel. Similarly to functional programming, there are no global variables. I will get the arguments and I do my effects on them. So it's destructive operation, but it's pretty much contained in the kernel. I compile this kernel from my REPL. I get the program. I can get the function as a high-level object, work with it. And finally, I invoke it by calling the launch function and just give it a grid of parallel hardware threads to compute it and give it the parameters, GPU array, of course. It finishes, and then I can check whether my computation was correct. Yes, it is, fortunately. It's simple, but it's telling. So much more complex operations are not that much difficult to implement in this way. If you do it in straight CUDA, then it's really, really difficult, even if you're not the beginner. So 3 main takeaways. This is interactive. There are lots of parallels with how we approach functional code. And we can mix and match low-level code that we write with the libraries that are already provided as we wish. And everything is interactive. Everything is feeling like Clojure. So I hope that you will try this and that you will find it interesting. Unfortunately, I think I run out of time. If I have some time, I will take questions now. If I don't, then, if we don't have enough time for all questions, I hope there will be many, just approach me wherever here and ask me whatever you like. I would love to answer whatever you need to know about it. So, have time for questions? Cool. So, should I pick someone? I know some people have questions, so who has questions? Just raise your hand, please. Oh, yeah. So, the first one.
Why you don't have a DSL for writing kernels? Don't you have a DSL for writing kernels?
Good question. So, I could have written DSL, or you could write a DSL and combine it with these functions, with these libraries. That would be a cool idea. But although it would be a really cool project, I don't feel it would be really useful in practice. So my main goal with these libraries is not to just show some cool technology. The main goal is for this to be as useful as CUDA for production. And I think it is, because there is no noticeable performance loss with this. So if I created a DSL, you would still have to learn enough C, because this is CUDA-specific C and OpenCL-specific C. And it's simple. So you would get, let's say, a Clojure DSL. You would have to know C, and you would always have to translate in your head, okay, how this DSL what C it produces. So I feel that you would just not get any benefit out of it. Although maybe someone will try it and maybe I'm wrong, but I don't think so. I wrote lots of code with this, and it is not a problem to write these C code because it's not really large, and you can try it interactively and see if you make some mistake, you can correct it right away. So it's not really a problem. Is it good? Okay, thanks. Another question. Someone in the back had. Okay, on the right. I think it was the first.
Hello. Do you think it would be possible to implement persistent data structures like Clojure's persistent mapping on the GPU?
Well, it would possibly be. I think, I'm not sure, but I'm not sure whether the hardware can support it. Probably yes, because it's Turing complete, but the performance would be disastrous. So the point of using accelerators and GPUs is to speed up code. So we could implement it, but it would be probably 1,000 times slower than on the CPU instead of faster. So it's not some magic technology that speeds up everything. Thank you. Someone else? Anyone else? Oh, some people on the back. Sorry, I didn't see you because of the light.
No problem. Hello. Are the Z parts testable within Clojure, or do you have to write own tests for the Z?
Excuse me, I didn't hear well your question.
Are the parts you wrote in C are testable by Clojure tests, or do you have to write your own tests?
No, you write only kernels in C. You have to call them from the Clojure host parts, and you write normal Clojure tests to test them. So I also wrote many. I think Neanderthal has something like 4,000 or 5,000 tests. So you can check how I tested Neanderthal to see, or Bayadera, or some other, or ClojureCUDA, if you're interested to see how to test these things. These are mostly integration tests, so you cannot test the kernel itself because it has to be managed from the host, but it's easy to write Clojure tests. Yeah. Thanks. Anyone else? Oh, another question on the stairs. Yeah.
Thanks for your work with all the stuff. So there have been some dueling with Neanderthal versus the Java version in, like, you have been blogging about that. So what's the current status? Which is the fastest?
Well, there's been some
dueling. You have been like chatting with the Java guys. So which is faster?
Yeah.
So
you can read the blog posts. I couldn't find any case where the Java library, Java GPU library and Java optimized library, they also use the same libraries that I use, Intel MKL and kubeless, but Neanderthal was faster in all cases where there was difference. In some cases they were the same. In some cases Neanderthal was faster. And I also have one blog post that I will publish soon. I just didn't have time to write the narrative. For mapping functions, Neanderthal is a lot like one order of magnitude faster for not so large arrays. But I will blog about it. So the point is, there were no cases where the other library was faster, and Neanderthal was faster in lots of cases. And it also supports AMD GPUs, NVIDIA GPUs, CPUs, whether the other library only supports NVIDIA GPUs and CPUs, and cannot combine them. In Neanderthal, you can combine CPU and GPU with no problem in the same session. Okay, thanks. Another question?
Yep.
Oh, so many questions. I'm so happy.
You're having time. We are ahead of time, which is amazing.
I'm ahead of time. It's impossible.
Yay.
Oh, yeah.
I'd like to hear your views on whether this is actually a kind of language question at all, because here we are extending Clojure with some native GPU code, and we could do that in very many languages, and also functional programming is possible in very many languages. So is it kind of, is there anything that Clojure brings in here? Or is it a language question at all? Is it just a kind of showcase of how to make efficient number crunching code in some programming language with functional features?
Yeah, I can agree with you. Anyone could have written something like this with this result in any Turing complete language, but I wrote it in Clojure, so. No, the point is, I think as much as I would like that it is about me and me being smart, I think is more like Clojure being the right language because it's simple. And I think important thing is that Clojure forces you to do REPL-driven development. So lots of experimenting, lots of feeling the tools, feeling the functions as they run. So it enabled me to have a really good feeling of when I write something, how it will compute. Maybe I could have written it in another language, but I'm not, probably not.
Okay, thanks, Dragan. One more. We still have time. I know
we have another guy. So
some people hate Q&A, but we're not here to please you. So
maybe to make an agreement, as long as there are hands up, I will answer the question if I have time.
You have time until 10 past 4.
Oh.
Dragan, which applications are you aware of that your libraries for number crunching are being used for?
Well, for now, only some close code that I use. But there are actually, each version that I publish on Clojure has more than 200 projects that included it. So some versions have 250, some versions have 150. And I guess maybe my estimate would be that at least 500 to 700 people included into a project and tried it. So how many of them use it for something serious, I'm not sure, or if any. But I use it for quite some complicated and serious stuff, and I'm really satisfied with the results. So maybe for start, it would be interesting for you to try it and see for yourself and compare it with other technologies. Do we have time for this guy?
Thank you for your talk. I'm just curious if you have a benchmark comparing to like C++ or C number crunching, like library or something similar to this.
Well, what is the point of this? When you write a kernel to run on the GPU and control it with Clojure, that kernel is in C, and the managing code is in Clojure and underneath in C. And the point is that the main performance is in the kernel, not in the managing code. But of course, you can lose lots of performance by writing bad managing code. And the point is, if you compare C++ as a language and C as a language, if you write your own C++ or C code without calling Intel MKL or CUDA, your code would be much, much slower than this. For example, if you try to write dot product in C or C++, just measure it, and try to call this dot product, it was on my computer 6 microseconds, on your it would be even faster if it's newer. This code even though you're calling it in Clojure, would be, I guess, maybe even 100 times faster than your C code, because these calls libraries that are optimized to the hardware. You cannot write this without being an expert that dedicated his career to these things. So it's the same. If you use these libraries from C or C++, you will get the same speed as this. So nothing noticeable would be lost in terms of performance compared to C or C++. Maybe in some really edge cases, but usually not any.
Okay, thank you.